Okay, so look at those uniform fields because they're quite accessible. Now let's look at something a little bit more complex. And the joyful thing is that you're only responsible for knowing the equations that we end up deriving. I'd like you to have an idea of where they come from, and we'll go through this step by step. But you're only responsible for knowing where these things, for knowing the equations at the end. So we said before that, and I'm not sure I justified it. I'm not sure I'm going to justify it. It's basically, we said before that my change in potential is equal to minus E dotted with S. And that's fine provided E is constant and E is constant with S. That's for a uniform field. But when the field is not uniform, then this little bit of ds, my little bit of length there, there's one electric field. There's another electric field there. There's another electric field there. Because as you go further away from this charge, you're getting into a weaker and weaker electric field. So it's like you're no longer on a nice flat level embankment. You're on the side of a volcano. And as you get further away from the crest, the ground gets more and more level. So what do we do under those circumstances? Well, under those circumstances, we're going to integrate this with respect to the changing, the little bits of distance. So we end up with that guy. And that's what we have here. Our change in potential is equal to minus the integral of E dot ds. And so let's apply this, and let's use a classic situation. So we have a positive charge at the middle. That is our mother charge. Remember, we're not talking about two charges here because we're talking about electric potential. We're talking about a charge and points of interest around the charge. Only one charge here. And my visualization for me is I have a mountain, a volcano, and I'm going from that point there, I'm going round the corner there. That's what this journey is about. So, okay. I pick a point of interest. So here's my point of interest. And I say, well, let's take that little bit of length, ds, that blue bit of length, ds. And I've got to know my distance of that point of interest from, or that little bit of length, from my mother charge. So there's my r. And then I need to be able to point to it. So there's my pointing vector, my unit vector in that direction. So for this point of interest, for this incident, I have my little bit of length. I have my separation. I have my pointing vector pointing towards it. And what I say is, well, if I remember back, the electric field at some distance from a point charge was KEQ over r squared times r. That's from last time or the time before. So then, if I want E dot ds, I want, well, KEQ over r squared times r dot ds. The unit vector is the vector, and I dot it with ds. Yep. This bit's just a magnitude. That's kind of nice. That's a magnitude. There's my vector bit. And there's my vector bit. So they're the bits I'm dotting together. Yeah? Well, here's the thing. The unit vector has a magnitude of 1. And the ds has a magnitude of ds. But you've got to modify them by the cosine of the angle between. And you can see this angle's here. This angle is there. Yeah, it's that little angle right in that corner. I guess the one disadvantage of this system is I can't make the diagrams bigger. Okay, but I can. ds theta dr. So that's that little triangle. Okay. Now looking at that triangle. This is the right triangle, and I know that ds is the hypotenuse, and dr is the adjacent. So cosine theta is equal to dr over ds. Agreed? Now, I made that triangle up. I just decided that's going to be a right angle. I'm going to draw a line at the top of it. There's my ds, and here's my dr. That's my dr is the little bit of radial distance you go. How much further are you away from the mother charge? Because that's what's the important bit. How far are you moving away? Not direction you're going. How far are you moving away? So if I rearrange that, I get this guy. So now that means that I can substitute in, and I get E dot ds is equal to KEQ over r squared. That's the magnitude. And rather than putting down dr dot ds, or 1 times ds cosine theta, I put down, rather than putting down, I can put down, rather than r dot ds, I can put 1 ds cosine theta, like I did there. So that's what I've substituted in there. And then I know, well, hold on, ds cosine theta equals dr. So I get that guy. So now I like that because my dr and dr, I'm talking about the same thing. Okay. So I say, well, my delta v equals minus the integral from radius b to radius a of E dot ds, which equals minus the integral of ke times q over r squared dr. Well, I know how to integrate something with respect to dr. I just go minus ke, that goes keq times r to the minus 2 dr. Yeah? And then goes, well, increase the power by 1 and put it in the denominator. That gives me that, which gives me that. And there's the take home. My change in potential between these 2 points, going from A to B, is equal to KE times Q times 1 over RB minus 1 over RA. Now, so there it is. I'm sorry, I'm trying to think of something insightful and it's not coming to me. So there it is. So what is the potential difference between 2 points? Between a point that is 3 meters north. So here's my Q. This is P1, which is 3 meters. And the second point is 6 meters to the south. Oh my word. P2. 6 meters. Well, potential difference is equal to, what we say, KE, Q. There's only one charge, so it can't be Q1, Q2, can it? It can't be big Q, little q. There's just one charge. And then what was it? Potentials go 1 over r, don't they? But this is a potential difference. Oh, I remember. 1 over r final minus 1 over r initial, which equals KE times Q. Q was 2 coulombs positive times 1 over 6 minus 1 over 3, which equals KE2 1 over 6 minus 2 over 6. Bad choice on my part of numbers. It's not so illustrative. Minus 1 over 6, which equals minus 1/3 KE volts. And I went from the northern slope quite high up to the southern slope quite low down. So did I go uphill or downhill? Went downhill, so negative sign. My potential is less at the end. Now, fair warning, you know, I can mess with you. So why don't I say, let's change colors on this so you know it's not the same question. Why do I say, oh yeah, I have a 3 coulomb positive charge, and point P is 6 meters at 70 degrees above the x-axis, and point B is 15 meters at 50 degrees below the x-axis, or at bearing 35 degrees and bearing 107 degrees. I can mess with this and give you a whole bunch of information about directions, none of which matter. The only thing that matters is how far you were at the end and how far you were at the beginning from the mother charge. So that's the physics gut thing. It's not being distracted by all this other stuff which is interesting and can come up in real life, but physics-wise makes no difference. Yeah. So watch out for that. Okay. Okay, electric potential at a point near a single charge. Okay, so we did this. My electric potential, which is V, the voltage at V minus the voltage at A, equals KEQ 1 over RB minus 1 over RA. And we find VB, Do you remember when we were talking about gravitational potential energy, and we talked about, well, MGH, and we said, well, that's really a cheat, that's not really U, it's the change in U. But that the problem was that people would realize that, well, hold on, if I have a table and it has a certain height above the floor, if I was to dig a hole, so does that bigger height mean that my potential energy of my block just got bigger? Yep. The answer is no, it doesn't, does it? It's like, I just changed my starting point. It mathematically looks like it should have got bigger, but I've not changed anything about the block. So, and you realize, oh, it depends on where I count 0 as. So then you go through this argument about, is 0 the center of the Earth? And then you say, well, hold on, 0 should be the center of the sun. And you say, well, hold on, 0 should be the center of the galaxy. Then you say, hold on, 0 should be the center of the local group. Then you say, I don't know anywhere apart from that. And I don't even know how far below me the center of the local group is. I have no idea how far that is. I have no idea. So what I do is I say, it's a fool's errand to try and find the bottom of the universe. Let's try and find the top of the universe. And we say, I know that if I go significantly far away from any mass, then as I go further and further away, my work done in lifting my object gets less and less and less, until eventually it's no work to lift it anymore. I have no pull of gravity on me. If I've got no pull of gravity on me, I can't do any more work against it. So the top of the universe, let's say, has 0 joules of energy. And so the bottom of the universe is measured in minus joules. Remember that? And so, like in chemistry, you measure electron energy levels by negative EV, because you start from the outside and work in. Yeah? So it's the same goes for this. A ruler's a ruler. I can put 0 on the floor and have positive numbers going up, or I can put 0 on the ceiling and have negative numbers coming down. The differences are always the same amount. So, okay, if this is my if I know the equation for the potential difference, why can't I find my potential by asking what's the difference between here and the outside, the edge of the universe, infinitely far away from all masses? Well, if my electric potential difference is given by this, why can't I get the potential of this, my voltage of that, by saying what's the potential difference between this point and infinitely far away from any charges? So that's the way I'm coming into this, yeah? Infinitely far away, no potential. Closer by, negative potentials. Yeah. So here's my point, here's my charge, and I'm going to compare this with infinitely far away. There's 0 volts here. I'm going to have some volts there. So I'm going to find my delta V between those two. Now, the way I do this is I go my RB and my RA, and my RA is this guy here. So I say, well, hold on. V, well, delta V is equal to VB minus VA, which equals KEQ 1 over RB. That's my final position, minus 1 over RA is my initial position. And this is infinitely far away. So I say, oh, that's 1 over infinity. Now, what does math tell you 1 over infinity is? They do. I'm really happy. Don't they say it's undefined? Or is that infinity over 1? No, it's infinity. Yeah, I thought they said it was undefined. That goes to 0. Okay? I'm going to edit that out of the tape, by the way. So V, my voltage at that point, is KEQ 1 over RB. It's like so simple. You know? It's like, it's beautiful. So when I go from, now look at this. V is equal to KEQ over RB. If I double my distance from the mother charge, what do I do to my voltage? I halve it, don't I? If I triple my distance to the mother charge, what do I do to my voltage? If I make this 3 times bigger, what happens to this side? If I make this 4 times bigger, what happens to this side? Is that an inverse square or is that an inverse relationship? So forces went as inverse or inverse squared? Inverse squared. Fields went as inverse or inverse square? Potentials go as inverse. And so will potential energy will go as inverse. Oh, by the way, if I wanted to find the potential energy of a charge here, Q2, I'd say my U is equal to Q times V, which equals Q2 times KEQ over R. Whatever this value is, just multiply it by the charge you are bringing from infinity there. Yep? Cool. What is electric potential at 0.3 meters to the north of a 2 coulomb positive charge? So we say, there's my charge, Q, and here's my point, P, and this is 3 meters. And I say my potential is equal to, well, this is what I say. This is what I say. I say delta V is equal to KEQ 1 over RB minus 1 over RA. So V is equal to KEQ 1 over RB. Because every time I write this down, I remember it a bit better. And this equation comes from there. If I know the top equation, I know the bottom equation. So this equals KE times 2 times 3, oh no, over 3 which equals 2 over 3 KE volts. Yeah? It's not bad, is it? It's like, it looks frightening getting there, but that's not so bad either. But in the end, you just get these equations. Now it gets frightening. No, I'm just joking. So, we've got 10 minutes. So let's say that we have a family of charges. So we're going back to having point charges. And I want to know the potential at this point here. All I do is I sum the potentials caused by each of these things. Let me ask you. I haven't mentioned this yet. Think about potential. Potential is energy per coulomb. Agreed? Is potential a vector or a scalar? What do you think? I'm gonna have we might as well have a quiz. So A, vector. B, scalar. What do you think? So it's energy per coulomb. So what do you think? Energy per coulomb. I'm going to stop it at 30. Come on, have a vote. Come on. Okay. Most people saying B, it's a scalar. Some people saying A. It actually is a scalar because energy is a scalar. And dividing a scalar by a scalar, coulomb's clearly a scalar. It's like mass. So it's going to be a scalar. So that means that actually, whereas before when we did our electric field, we had to worry about the direction of these things, they just got values. So we're just going to add these things up. So we just say, oh, the potential at that point is equal to, you know, the sum of these things. So let's see. Okay. Do I do an example of that? Okay. Consider 2-point charges that are separated by a distance r12. So what goes on now? What we say is consider potential energy of a pair of equal. So now we're doing. Oh, okay. I'm gonna stop for a second. I'm gonna do this. I'm gonna do that. Oh, it starts again. That's 9 and 9. Okay. I'm gonna go to a pen. Can you work out for me the potential? Can you do that for me? I'll do some hints. Well, the big hint is that V equals the integral, or if you like, the sum, let's say the sum of KE, what was it? Q over R. Yeah. And that equals. Oh, I got no answers for you. So we'll do it together. So that's KE is a constant, so that can come out of the summation sign. QI over RI. So then I go, okay, that's KE. I've only got 2 of them. It's going to be 3 over 4 plus, because it says add them, 2 over 2, which equals KE 3 over 4 plus 4 over 4, which equals 7 over 4 KE which equals 1.75 KE, and what the unit's going to be? And I can dress it up, can't I? I can give you IJKs and you work out the magnitudes, or I can give you distances and directions. I can make it look, oh, I can do, 7 meters, and this is 27 degrees, and this one here is 2 meters, and all that counts in the end is what is the charge and what is the distance, and all this separation stuff is just nonsense. It's just to throw you off, okay? So I can stop that now because it was like, okay. Okay. We can go a step further and we can say, okay, so let's not talk about potentials, let's talk about potential energies. Okay, and again, you're not responsible for getting here, you're just responsible for knowing what you do when you're here. And what we do is we say, well, the potential energy is equal to the charge that we add multiplied by the potential of the point. So this charge causes a potential here, and we put that charge there. So it's just one step beyond what we've done. If you can figure out the potential at that point, and I tell you there's a 3 coulomb charge there, just take that potential and multiply it at that point. So if you think about it, it's going to be, well, V was equal to KEQ1 over R12. I like big Q's because it's like the mother charge. So then U is equal to the little charge times the V, which is the little charge times the potential caused by the mother charge, which is that. Does that make sense? It looks like, where did that come from? It just came from multiplying the potential by this little charge. And so it's not so bad. And that's how you remember it. Supposing we have a whole bunch of them. We had 3 charges. Well, there's potential energy due to that pair, and there's a potential energy due to that pair, and there's potential energy due to that pair. And so we end up with Q1, Q2 over the separation, plus Q2, Q3 over the separation, plus Q3, Q1 over the separation, whatever it is, just the pairs, yeah? It's that pair divided by that separation. It's multiplication of that pair times that separation. It's multiplication of that pair by that separation. So it's kind of not bad. We've got, well, let's have a quick look at this. Can I get to the end? Not really. Is it a good point to stop here? Yes. I'm going to draw a line there. We're a little bit behind, but I'm going to draw a line there. And next time we'll continue.